Okay, the purpose of this video is to look at our last big integral application. This topic actually goes pretty deep. It's about finding volumes, and there's actually a decent amount to it, but we don't have time to get into the nitty-gritty, and it's difficult to do it on this online format. So my goal is to just sort of introduce this idea to you of being able to use an integral not just to find area, but to also find volume. So a big thing in calculus is using integrals to not just find areas, but to find other kinds of measurements, like the volume of something, or it can find even higher dimensional volumes, if you will. So you can find like the amount of space, quote unquote, a four-dimensional object takes up, wherever. So integration can be extended from the two-dimensional example of area into other realms. One of the big things for us living in a 3D world is being able to extend it into volumes. So I want to just introduce you to that so you have some idea in case you're taking our calculus course that, hey, it can be used in this way. Like I said, we won't go into too many of the details that we would have if we had been in class, but at least you'll have seen it, all right? So the goal here is to be able to find the volume of something called the solid of revolution. And we'll talk about how to find that volume and kind of the concept behind it. And then from there, if you see it again, you can hopefully start, they basically start modifying what they revolve it around, and different curves you can use and curves between curves and stuff. I'm going to keep it simple and basically take a curve and show you how to revolve it into a 3D shape and find that thing's volume. All right. So let's talk about what is a solid of revolution. Well, solid of revolution is formed. It's a three-dimensional figure. How is it formed? Well, it's formed by taking a two-dimensional figure and rotating it about a line, about or around, whatever. So here's an example of, like, here's somebody's rectangle, and here's like the x-axis, and somebody took this rectangle and pretend you start spinning it around the x-axis. So you could picture this was like this rectangle was glued onto like a stick. Start spinning the stick really fast, it would trace out this cylindrical volume. So it's actually possible not only to use integration to find the area of the shaded region. Actually, you wouldn't need integration because it's a rectangle, but whatever this shaded region is, you can find its area, and then you can spin it around. There's a calculus method then with integration. Not only could you find the area, you could also find this volume of revolution. Now, volumes of revolution can be simple, like this rectangle spins around, becomes a cylinder, or you could have weird funky shapes, and then they can make things that like almost look like a vase or something like that. All right, so this is what a solid of revolution is: a two-dimensional area that sweeps out a three-dimensional volume. So just to make some common shapes, some of the ones you know can be formed this way. So like here's a semicircle. If this semicircle were rotated around that horizontal line, it would trace out a ball, or what we call in math a sphere. This triangle tends glued to this line and spun around that line, it would create a cone. And then this rectangle kind of floating in midair here would sweep out a cylinder, but then this inner part, it wouldn't sweep out the inner cylinder. So it basically would be like a hollow cylinder, a cylinder with another cylinder bored out of it. Using our method, we could actually find the volumes of all these. So actually calculus, and I wish we had more time to do this because I said we would have done in class. One of the things calculus does very easily is finds the volume of a sphere for you. That volume 4/3 pi r cubed that you see definitely in high school. You might even run across it in middle school. Nowhere tells you how someone found that. And the first person encountered was a guy named Archimedes, and he didn't actually use calculus, but he used a method that was really close to calculus. In fact, it's too bad things didn't go well in Greece a little longer, because he was really close to developing calculus, and they would have had it back then, but it wasn't meant to be, and Greece fell, and it took a while. It took quite a while longer until society came back and someone developed calculus. But basically, the method he used was very close to calculus, and calculus can very easily prove that weird formula. So unfortunately, we don't have time to look at that, but just realize this method is able to prove things like what is the volume of a sphere, volume of cone, things like that. All right. So we could form the three different volumes of revolution from these. So we want to go, how do we find these volumes? So say we had something like this, like here's a volume of revolution. Here's sort of the cross section of it. If you took this cut off piece with the U in it and then spun it around, you could imagine getting this shape, this sort of three-dimensional spindle-looking thing. Knowing the area of this can help us find the volume of this. So we want to know, how do we take this area and form a volume? Now we know we could get this area, as long as someone gives us the function, we could get this area by integrating from whatever number this is to this number. So if we integrate this from A to B, we would get the area of this region. How do we use that area to then spin it around and get the volume of this thing? Well, this is going to be a little bit technical, so I'm just going to kind of go through it quickly to get to the formula. But it basically involves taking this thing and sort of applying a circular formula to it, like something to turn this into the circles. So the theory that sort of proves it thinks about it as Riemann sums. Remember, so we did this before. Say we have the curve. We could approximate the area of the curve using these rectangles. The more rectangle, I only picked 6, the more rectangles we use, the better the area would get to this thing. Well, someone sort of did the same thing for the volume. They go, well, if we want to get the volume of this smooth curve-looking spindly thing, we could just break it up into the approximate rectangles and rotate each of those rectangles. Right? So I could take these, rotate them around, and it would give me a bunch of cylinders. Now, if you wanted to approximate the volume, you'd have to add up all these cylinders. But it's actually a bit easier than just doing the cylinder formula. And here's what happens. You want to make these cylinders thinner and thinner and thinner, right? If you had more of these rectangles, it would be closer to the curve. Well, if you made these slices thinner and thinner and thinner, you'd have more of the cylinders and they'd fill in more smoothly, and you'd approximate the volume of that thing. So basically, we want to go, well, what do we want to do with these is essentially find what the volumes of the cylinders would be and then shrink them down to have almost no height. Basically make them like circular discs and then add up all the circular discs. All right, so I'm going to show you how we would have found these rectangles and then apply it to here, and then you'll see the formula. So this part's a little technical, but it'd be nice if this computer will work. So to find the rectangles, each rectangle we would do the height times the width. So each one of these bases is change in x, and the height would be whatever that x sub I star, whatever left, right, end point, whatever we use. We use points that were on the function, maybe that one, that one, that one, and use them to make these approximations. So to find the rectangles, we would have to do basically the function height times the width, which we called f of x sub I star and change in x when we were doing them, doing the Riemann sums. In order to turn this into a cylinder formula, what would the cylinders be? Well, cylinders are, basically you can think of this as the radius of each one of these cylinders. And how do you use the radius to find a volume of a cylinder? Well, the cylinder would be the area of the circle, pi r squared times the height. So this is basically the cylinder formula, pi r squared h. Now, the height of each one of those cylinders is that change in x. So then the rest of the formula is the area of the circle. How do we get the area of the circle? Well, we got to take the function height, which is the radius, square it, multiply times pi. So basically, this is the rectangle version. This is taking those rectangles and turning them into cylinders. So basically, it's taking the function, squaring it, putting pi on it, but that change in x is still there. So now, the rest of this is a bit technical, so I'll talk through it very briefly. What do we do with the rectangles? We want to add them up. So this is the Riemann sum. What do we want to do with these cylinders? We want to add them up. So we want to add up n of them. Then what do we want to do? Well, we don't want just 5 rectangles or 7 rectangles or n rectangles. We actually want infinite numbers of rectangles. So we end up taking the Riemann sum, like what we did here, is we have this approach infinity. The more rectangles we make, the better our approximation. So we do the same thing in this formula. The more cylinders we make, the better our approximation. So then, in calculus, we had a way of representing this. If we basically found, quote unquote, infinite rectangles and added them up, it became the exact area, the integral. The only difference between this formula and this formula, as you might notice, is there's a pi in it, but the pi is allowed to come out of the summation and out of the limit, so the pi can come out front. So what's left behind is the summation of the function squared change in x. The change in x becomes the dx, and the only real difference is that squared's there because the pi was kicked out. So this tells us if this is the area of the shaded region, how do we get the volume of revolution? All we have to do is basically throw this function into the area of a circle. We're going to take the heights and square them and multiply them times pi. So it's kind of like pi r squared. All right. So if this is your area, this is how you can rotate it and turn it into the volume. All right. So the area being this thing, if we know this thing's area, we square the function, multiply times pi, and do, I should say square the function, integrate it, then multiply times pi. It'll give us this volume. So here's the formula. The technical stuff's over, so you can be happy. So here's the formula. If you want the volume of a solid of revolution, and I'm keeping this quote-unquote simple, solids of revolution, you can revolve around any kind of line. This is specifically for revolving around the x-axis. So if you want to find the volume, so you have some area, you have a function, if you can find its area between the curve and the x-axis, you can spin that around to form the volume by using this formula. The volume will be pi, the integral of the start and end, and then whatever function squared, and then the little dx, all right? So from here, it's just a matter of showing how to use this formula. The formulas can sometimes by hand be tricky to do, but once again, since it's an integral application, you can just throw the setup into the calculator. So the big thing is going to be setting this up, all right? So the example I'm going to show is basically going to have this volume formula, and I'm going to be given some function and some starting and ending point, and I'm just going to have to plug it into this. And once again, sometimes you can solve them by hand. Other times, the calculator may be handy. So, like I said, feel free to use the calculator. In fact, one of the examples I give you, you might have to use the calculator because you may not be able to get the antiderivative. All right, so this is the example I'm going to do, and then I'm going to break this into two pieces, this video. So I'm going to talk about this, and then in the next video I will show the solution. So the example is to find the volume of the solid of revolution that's obtained by rotating the region under y equals square root of x about the x-axis from 1 to 4. So to get an idea of what we want to do is I'm going to need to draw a picture of this. It always helps to have a picture. I want to draw the square root function. I want to see it from 1 to 4, and I want to take that section, rotate around, and think of what this is going to look like. All right, so think about it a little bit, see what maybe you could set it up yourself and try to get it. But if not, like I said, the next video will have the solution, all right? But I figured maybe you might be able to try it yourself, because if you can just plug in, figure out what the a and b is, what the function is, throw it into a calculator, you should be able to get. But like I said, I'll give the solution next video. But like I said, try it yourself. See, try to at least set up the integral if you don't have a calculator. Set it up and see what you think it would be. All right? So I'll give you time to do that. And like I said, click on the next video to see the solution.